Hi, my name is Zach Wakeman. I'm the Biodiesel Lab Manager for the School of Environmental Sustainability at Loyola University of Chicago. And we're standing in the Searle Biodiesel Lab. It's my pleasure to give you a brief tour today. So the biodiesel program at Loyola University started in 2007. It started as a class called Solutions to Environmental Problems. This course aims to let students work on tangible environmental issues that the university or community is facing. The very first topic that we worked on was biodiesel, to address the emissions from our transportation, specifically the shuttle buses on Loyola's campus. I was lucky enough to be an undergraduate student in that class in 2007. I then went on to intern for the biodiesel class before getting hired on to help turn that class project into a standalone education program and hands-on experiential learning opportunity for our students. Years later, I got my MBA from Loyola, and I've had the pleasure of working here ever since. So I'm going to give you a little bit of an intro to biodiesel and our biodiesel production process as I walk you through the lab. So the Searle Biodiesel Lab, which we're standing in right now, was built as part of the School of Environmental Sustainability in 2013. Prior to that, we operated out of classrooms in Damon Hall, a building that's been torn down now. Then we were in a drywall box in a warehouse on Broadway Avenue where the mailroom is now. This was a small space. It was about the size of the lab prep area and my desk that's behind me now. That's where we used to do all of our production and teaching. That was storage space and research. Everything happened in there. When we moved into the School of Environmental Sustainability and the Searle Biodiesel Lab, we were really able to greatly expand both the scale and the scope of our project, producing more biodiesel fuel and looking at ways we could pursue our ultimate long-term goal of being a zero-waste production facility. So everything starts for our process with a waste product on our campus, the used cooking oil coming out of our campus cafeterias. So when we're done deep frying with oil, making French fries and chicken fingers or whatever else we're going to make in there, that oil eventually goes bad. It starts to go rancid, at which point it's no good for cooking anymore, but it's still perfectly fine to make fuel out of. And so we're able to collect that used cooking oil, not only from Loyola's cafeterias, but also from all of the major universities and museums in the Chicagoland area. So behind me here is some of the used cooking oil that we have dropped off by individuals. They come from the Rogers Park and Edgewater neighborhood, but also from all over Chicago to make sure that their used cooking oil or expired cooking oils are going to a good use. The first thing that has to happen to all of this used cooking oil is we need to remove contaminants. Specifically, we need to remove food solids, so breading and bits of chicken fingers and stuff like that. That needs to get filtered out or settled out, and we're able to direct that byproduct to anaerobic digestion at wastewater treatment facilities. So this is a composting-like process, but instead of being in the presence of oxygen and aerobic microbes, it's done underneath a layer of water. So little or no oxygen, and it's anaerobic microbes. They're able to deal with the oily substance that the aerobic composting wouldn't normally be able to deal with. And so by partnering with wastewater treatment facilities, we can send our oily kind of organic matter we've removed from the cooking oil to anaerobic digesters, where it gets turned into high quality nutrient-rich fertilizer and natural gas. So it gets turned into energy. So after that happens, then all of the used cooking oil gets loaded into this large storage tank behind me. You'll see a bunch of logos from universities, museums, and restaurants. Those are all folks that are donating oil to Loyola. It gets picked up from all over Chicago as part of the Loyola Oil Collection Network that's run by Green Grease Environmental. So they're our contracted partner to help collect all this used cooking oil and bring it here. After everything, all those solids get filtered out, we still have some chemical contaminants that we need to track and adjust our chemical reaction to deal with. Those are going to be free fatty acids. These free fatty acids form in the oil when they're in the presence of water and high temperature for a long period of time. That happens in a deep fryer because we've got a lot of water content in our food, specifically in potatoes. They have a really high water content. So we have a bunch of water that's going to dissolve into our oil. It hydrolyzes the oil, and we get portions of that oil molecule, fatty acid chains, that break away from the triglyceride oil molecule. And those free fatty acids can get turned into biodiesel, but not in the process that we're running at Loyola. So at Loyola, what we need to do is monitor those free fatty acids, ensure that we're keeping that level low by keeping our used cooking oil fresh, kind of having a high inventory turnover. And then we're neutralizing those free fatty acids with some additional base catalyst, turning them into soaps, and we're going to be able to utilize those soaps later on, which is awesome. So once we're ready to start using this cooking oil, it's going to flow through that yellow pipe that's behind me. The yellow pipe goes overhead. Hopefully you can see it a little bit right now. That pipe going overhead is eventually going to run over to our reactor tank here. So our reactor is where we're going to put that used cooking oil. We're going to start heating it up to 60 degrees Celsius, which is degrees Fahrenheit. Nobody cares. It's science, right? We use Celsius. In this tank over here, in that orange tank, is where we're going to mix up our chemicals for the reaction. It's going to be methanol and potassium hydroxide. We have a couple options on catalysts that we can use. We specifically choose potassium hydroxide because the catalyst isn't used up in the reaction, right? A catalyst is there to facilitate the reaction. We want that catalyst to be useful later on, right? We don't want it to just be a pure contaminant we need to deal with or something that we need to remove later on. We'd ideally like it to be beneficial. So by choosing potassium hydroxide, it ensures that one of our byproducts further down the line in the process is going to be able to be more easily utilized on campus. That's great. So this is purposeful design all throughout the process. So our methanol and potassium hydroxide are mixed in that orange tank. Those are then mixed with the hot oil at 60 degrees Celsius. It's not burning hot, right? It's a nice, a nice warm temperature. So that mixes then in our reaction vessel. What's happening during this reaction, the reaction is called Trans-Esterification. What's happening is the glycerin backbone that's holding on to three fatty acid chains, forming a triglyceride molecule. We're removing that glycerin molecule. We're stabilizing those free fatty acid chains with a methanol grouping, and then the glycerin is separated and free. It's more dense than our newly formed molecule. The new molecule is fatty acid methyl ester, which goes by the common trade name biodiesel. So the glycerin is more dense than our biodiesel, settles down to the bottom of our tank after we're done mixing, and we'll go ahead and remove that through this black pipe here. It gets set aside into a tank for later. The biodiesel at this point is kind of in a crude state. It's not ready to get used yet. It still has some contaminants. The reaction didn't happen perfectly. There were some byproducts that might be left over, some side reactions that might have happened, and we need to go into a little refining so that we end up with a highly refined biodiesel product. So the biodiesel is going to flow through the green piping here, and it's going to go into our second large tank. This is our methanol recovery unit. It's essentially a large alcohol still. We're going to heat the biodiesel up even further. We've got a few different options for heating in the lab here. The large green kind of vertical column here is an electric heater. It's a high voltage electric heater, so we're able to utilize electricity for heating. This can be really great depending on where we're getting that electricity from. So as we continue to purchase more and more of our electricity at Loyola from clean sources of energy, all of that electrical heating, right, is coming from a clean source. That's great. But we also have the option to heat this process with the boiler in the building. So this dark blue piping is connected to the boiler system. That boiler system in the building is preheated using our geothermal system, and then can be further supplemented with either natural gas or biodiesel. So we can actually burn biodiesel to create the heat we need to make more biodiesel to run further processes. So we've got a lot of different options that we can play with to find the most efficient process for us. So as we're heating up that biodiesel more and more, we're driving any methanol that's left over from a reaction, right, into a vaporous state. It's going to go up into these condensers up here, where it's going to get cooled down and turned back into a liquid. That collected methanol liquid, that recovered methanol, is going to end up in this second orange tank, where we can test it and reuse it. Awesome, right? The light blue piping up here is what's doing the cooling. All of the cooling is being powered by our geothermal system. So we're using the natural temperature of the Earth to provide all of the cooling that we need. During the summertime, that excess heat can kind of just go underground and dissipate. But during the winter, it's even better. The excess heat that's pulled off of our biodiesel process goes into our geothermal system, which is distributed throughout the School of Environmental Sustainability building, and it dissipates into the building to help heat it. So the excess heat off of our process is actually helping to heat the building. Very cool. So then the biodiesel makes its way to our final processing tank here. This is where we're going to do the final refining. We're going to use the world's most magical substance to do the final refining on our biodiesel. The world's most magical substance is water, right? Water has so many unique properties, and the one that we're really interested in is its dual polarity. It has a positive charge and a negative charge on the same molecule. It's got dual polarity, brah. That's my worst joke, I promise. Okay, maybe not. We'll see what happens. So it's got dual polarity, so a lot of things are attracted to it. It makes water the universal solvent. So most things are attracted to water, but not oil, and biodiesel is an oil product. So we're able to use that as well as the density of the water. The water is more dense than the oil, right? Oil floats on water. So we spray water into the top of the tank. It wants to sink down to the bottom. As it does that, it attracts contaminants, the things that are not oil, and it draws them down to the bottom of the tank for us. So we do this in a slow process, adding little bits of water, letting it sink down, drawing our contaminants out. That gets set aside in this tank, and it's a really efficient means for us to remove any final contaminants from the biodiesel. We set this aside, and we're going to go ahead and try to use that and use some of those contaminants getting pulled out of the biodiesel as well. Right? A contaminant is just something that we don't want in our product. Just because it's a contaminant for biodiesel doesn't mean it's not useful. Not that we can't make something useful out of it. We just don't want it in our biodiesel. So once the biodiesel has all of those final contaminants washed out with water, we'll pump in compressed air, which will help to remove the final water, help it settle out of the tank. Then the biodiesel is going to go overhead through the green piping. Hopefully you can see that again, and end up in our storage tank. From there, it's ready to go out and go into any diesel engine. It primarily goes into the Loyola shuttle buses. There's a lot of testing, though, that has to happen all during this process. And all that testing happens in-house here at Loyola. All of these things are run by undergraduate students, from the production, the equipment maintenance, and the chemical analysis testing. So all along the back wall here, along this back bench, we're going to be doing quality control testing on the biodiesel to ensure that it's going to meet high industry standards, that the reaction happened efficiently, that we removed all of the contaminants, and that it's going to work well in a diesel engine. When we put it into those Loyola shuttle buses, it's going to work really well. So here's another view of the reactor behind me, right? That's the wash tank. As we walk this way, there's the methanol recovery tank, and this first tank over here is the biodiesel tank. These first two tanks, right, this reaction tank and the methanol recovery tank, they've got a shiny insulation cover on it. Those are heated processes, so those are heated tanks, and they're insulated, and then the shiny stainless steel cover you see is an insulation cover. The wash tank down here at the end that has the Loyola crest, that's not a heated process. We want the heat to dissipate at that point for that to work really well. And so we let the heat dissipate out of that. It's not insulated, and so that's why it looks a little bit different. The other cool stuff that we do here in the lab is focused on being the zero waste production facility. So we take that glycerin byproduct and we turn it into the soap that's used at the university. So this stainless steel vessel behind me is what we use to make soap. We take that glycerin byproduct, we remove any excess methanol that's left over in that glycerin, and then all of the other things that are making our glycerin fairly low quality compared to pure glycerin, they're actually really convenient contaminants. they're contaminants if you're looking at pure glycerin, but if you're looking at turning it into soap, they're actually all ingredients for making soap, which is great. So instead of putting extra energy and chemicals into cleaning up this glycerin, instead what we're doing is using it as is. We're going to go ahead and utilize those ingredients in the glycerin and turn it into the foaming biosoap that's used across our campuses. Right now, the biodiesel lab is being utilized for hand sanitizer production during COVID-19. So we're using some of this space and some of the equipment to produce hand sanitizer and surface sanitizer. But we really look forward to having students back on campus to really restart some of the biodiesel operations and continue exploring the new things that we're going to work on. All of the stuff that we do in the biodiesel lab is run by students. All of our projects are student ideas that are developed over the years. It's a really exciting place to be, and we look forward to seeing everybody back here again soon. Bye!